All right, so we are now transitioning from just thinking about ketones and aldehydes to looking at the other carbonyl functional groups as well. So esters, carboxylic acids, and amides. And it turns out that this equilibrium is going to be extremely important while thinking about how those reagents that we've already talked about are going to react a little bit differently with this with these new types of functional groups. So to start things out, I always just ask this open-ended question: which side of this equilibrium would be favored? So in class, we would have done it as a clicker. Is it the right side? Is it the left side? Or is it neither? So it would be about 50-50 if it's C. So take a minute, think about that. Pause the video, decide for yourself. All right, you've done that. Hopefully, most of you said neither. What are we good at looking at the stability of? Anions, or essentially ions in general. If we have something positively charged or negatively charged, it's relatively easy for us to say, oh, it falls here on the periodic table, it's either stable or unstable. And what we have here is a negative oxygen over here. And we also have a negative oxygen over here. So essentially, the anions are equivalent, and they're going to be similar in stability. So this equilibrium is going to be a very important one where both sides are going to exist, and that's going to impact our reactivity with these different reagents that we've talked about with ketones and aldehydes. Now we're going to talk about all of them with the other functional groups. And so we talked about ketones and aldehydes. Now we're moving on, and we'll be talking about carboxylic acids. We'll be talking about esters, and the last one we'll be talking about amides. And we're essentially going to run through them in the same kind of order that we did previously, where we talked about the reductions with sodium borohydride / lithium aluminum hydride. Then we're going to move on to those different organometallic reagents that we discussed previously. But another question we might have is, well, how do these compare as electrophiles to those ketones and aldehydes? And we're going to talk about that right now. All right, we've talked extensively about ketones and aldehydes as far as their reactivity as electrophiles. Now we're moving on to those other functional groups, and we have to ask the general question first, which is more electrophilic, the ketone or the ester? So pause the video, take a few minutes to think about this, and also draw some structures. This is a hard question since we haven't really talked about it before, but you have all the tools to figure it out yourself. It's just going to be a little bit of work. You got to draw some things out. You got to think a little bit. So do that right now. All right. So what we have to think about is kind of the amount of partial positive charge on the carbonyl carbon. So is the partial positive larger here or larger there? And to really figure that out, we have to really look at the full character of each of these molecules. And how do we do that? Well, we can't just represent these molecules with one structure. We have to look at all of the structures that represent this. So that would be the resonance structure. So for ketones, the only viable resonance structure, and it's the same situation for aldehydes, would be by just pulling up those electrons onto that oxygen. That would generate the oxyanion and the cation on the carbon. So we've talked about these before. This is the better resonance structure. Everything's got an octet, but what we said before, and the reality of the situation is maybe this is 70 to 75%, we'll just say 70% of the character up here, and about 25% of the character down here. So that's all we have here. What about the ester? If you haven't yet, draw them out yourself. Pause it right now, draw them out, and then come back. But you just did that, so that's good. So we can do the same thing we just did. Pull those electrons up to the oxygen. And is that it? Are we done? Or is there another resonance structure that we could draw? Yeah, that other oxygen should be conjugated with that positive charge as well. One of those lone pairs will be in the p orbital, allowing it to donate them, making a double bond there. So we have 2 resonance structures over here. We have 3 resonance structures over here. And now that we see those 3 resonance structures, this is the major contributor here, but there's both of them present. What's the worst resonance structure of these 3? So again, pause the video, think about that. Which one's the worst? And then come back. All right, you did that. This one's the best. Everything's neutral. Everything's got a full octet. So which of these is worse? So we got to go in order of the most important to the least important factors in evaluating resonance structures. The most important is the more bonds, fewer charges is better. And I like to really think more about the idea of everything having an octet. Does everything have an octet in both of these? And this one, everything has an octet. The oxygen is fully saturated with electrons. The carbon is, the oxygen is. This one, this carbon's lacking its octet. So this is the worst of those resonance structures. So where the resonance structure for the ketone, where the positive charge was on that carbon, was about 25% of its character. Since this is the worst resonance structure, if we think about these, this is still going to be almost all of the character. It's going to be similar to this, where like about 70% of the molecule's character is its major resonance structure. But that additional, this says 25%, that doesn't add up to 100. We're going to say 30%, not 20%, 25%. That extra 30% that we had in one structure here is going to be divided between these 2 structures, and the majority of that is going to be on the more stable structure. So we'd say that maybe 25% of the character of this molecule is in that structure, 5% is in this structure. So essentially, which of these molecules is more electrophilic? Well, which one has the greater partial positive? Remember, electrophiles, we often write them as E pluses. And essentially, we're looking at which carbonyl carbon has a greater partial positive. And essentially, by evaluating our resonance structures, we can see that this is a pretty minor contributor of the 3, whereas this one's the only other resonance structure and it still has a lot of character. So this is the more electrophilic. This is more electrophilic than any of our other new functional groups that we're looking at. Esters, amides, carboxylic acids, all of them are worse electrophiles, so they have less partial positive on that carbonyl carbon compared to the ketones and aldehydes. Because they have an electron donating group right next to that positive charge, the positive is not going to be very big if we have an oxygen or a nitrogen right next to it donating electron density to it. So hopefully that makes sense. All right. So we're going to move on to the reactions of these molecules in the future videos.